Hello, my name is Doğan Alcı. I am a master's degree student at Gebze Technical University on Department of Computer Engineering. Today, I will tell you about our work that we did with my advisor, Yusuf Sinan Akgül, called Human Action Recognition with Raw Millimeter Wave Radar Data. In the presentation, first I will define the problem. Then I will present the related works and our solution proposal. Finally, I will show our experimental results and the work we plan to do in the future. In this study, we recorded human movements using raw data of Texas Instruments IWR 1843 mmWave radar. Then we transformed this rare data into a multi-channel, multi-dimensional structure that we named VDAR. We use this VDAR data to train our CNN network. With our real-time test environment, we tested our model with both real-time human movements and the test data we recorded. Detection of human movements is an important issue in many areas. In automotive industry, detecting the action both drivers and pedestrians will prevent accidents that may result in injuries or death. It also can be used in many applications such as child presence detection, monitoring of vital signs such as sleepiness, or monitoring of passengers. It can be used to improve applications such as retail stores and security systems. Rehabilitation treatment must be monitored and controlled by an expert with feedback. With motion recognition, patients can perform movements correctly and the need for an observer can be eliminated. MMA is a special class of radar technology. And FMCW radar transmits a signal with a wavelength in the millimeter range called a chirp. It's a sinusoid whose frequency increases linearly with time. This system can determine the range, speed, and angle by capturing the signal reflected from objects. We can classify related studies into three categories as variable technologies, computer vision, and processing of sensor data. Ways detecting sitting and turning moments. He proposed to reconstruct the skeleton from RGB images. Abate and V detected motions by using sound, accelerometer, and EEG sensors. By using MMA radar's point cloud data, Palipana, Lee, Sine, and Liu estimate some human behaviors in their studies and use two different types of sensors and map them together to detect 19 human joints in their study Mars, which is very interesting. Studies aiming to recognize human movements, process biometric data, and cause serious privacy problems. In the survey we conducted with the users, we saw that people do not want these devices around them. Actually, they feel like they are being watched. These devices are very sensitive to light and location. They are rough, bad-looking, and far from the decorative concept of our living spaces. In addition, point cloud produces very limited data about the environment. In this study, comprehensive data about the environment, background, and human movements were collected with raw data of MMA radar. This data does not contain biometric information and is not dependent on light or location. It also takes up very small place. Texas Instruments provides researchers tools to capture and store all information. By using these tools, the information obtained from the MMA radar can be easily processed and the resulting point cloud, which contains coordinates, angle, and velocity values are calculated for each object, becomes ready for use. In the study, instead of using this point cloud, like related works we talked about before, we used raw data obtained from antennas. The point cloud does not completely capture the background. However, it does not show all the body parts. It gives only one coordinate of the detected object. It has been observed that there are errors in the detection of non-moving or fixed objects. We use Texas Instruments DCA1000 EWM data capture card to record all the data appearing on the LVDC lines with speed of 1 gigabit. We transformed this raw data to a new image-like form and named it VDAR that we will talk about in a few seconds. To explain VDAR working structure, assume that 16 data came from single TX antenna where T0 is the time that first signal received with RX0. In this case, 4 RX antennas will capture 4 different signals in each n time slot. The experiment participants makes a certain moment at the same period of time. VDAR program takes these 16 data as a pipeline. To make it clear, assume that our data is shown in figure 12. Due to its pipeline structure, it processes each data one by one into a multi-channel, multi-dimensional structure, which dimensions were previously sent as arguments. Pipeline works in first in, first out method, so it starts entering values from the upper left corner. It means upper left corner is the value of Rx0 in time of T0. After that, raw data will be converted into VDAR. In order to fit the architecture of the models we use, we calculate the largest square size to be created according to the size of the data obtained during the enter motion. The output is this large square size, which we later rescale to make experiments on AlexNet or VGG16 networks. With the visualization method VDAR, we propose representing the data generated in the sensors at a time period. We named this method VDAR, inspired by data obtained with the radar like a video. Actually, VDAR shows the environment information in a period of time in a single picture frame. The reason for making it square is to ensure that the model is robust against input differences such as different frame numbers or different number of chip signals. By making this raw data transformation, we achieve more generalized results. MMWave Studio cannot automate real-time recording. That's why we run an additional data collection program in the background. With this program, moments made in certain periods are automatically recorded to the files containing the labels. A total of 840 data with size of 30.1 gigabytes were recorded from 5 different users. We use 800 for train and 40 for test. We create a test environment in order to test our models in real time. We recorded the moments using our data collection program. These tests enable our network to generate ideas about how it produces results from data obtained from different conditions. It also guides us to make the necessary improvements. After data collection processes are over, we need a network to feed by VDAR data. First, we create a CNN network which has 3 convolution layers, 4 neural network layers. We train the weights and all parameters from the beginning. Model produced results with high accuracy at the end of the training process. However, we observed that our model produced bad results on the validation data. By keeping the network that we have trained from the beginning on one side, we tried to train only the last layer of VGG16 network without changing all its parameters except the last layer. In the study, approximately 50,000 parameters in the last layer were trained by keeping all other parameters constant. We used Adam as optimizer, trained the model for 18 epochs with learning rate of 10 to the power minus 6 and set batch size to 8. We used the couple validation algorithm with k-value of 8. This allows us to learn more about the content of the model and also allows data to be used with both train and validation phase. So we can calculate mean and standard deviation results of all iterations. The model we created was trained with this data and model tested both test data recorded before and real-time moments. It has been observed that VGG16 fine-tuned model completes the training processes with much better results. The test and validation results were very close to each other. By looking at these results, we can say that the learning process is much healthier than the first model. As seen in confusion matrix, the estimates for the moments are close to each other for each class. Table 2 shows the real-time predictions results for moments made in real time. Our accuracy rate is over 90%. In the next phase of our work, we will use VDAR data with LSTM, RNN, and transformer networks. Due to the instability of the data transfer rate, we cannot obtain the number of real-time tests per second. In our future studies, we will calculate how many tests we can perform per second. We need to increase the amount of data in our datasets. We plan to have data obtained in different conditions with more motion classes. We will implement a new augmentation technique that we are currently developing into the dataset and observe the effect on the results. To summarize, we focused on the rave data generated by mmWave radar antennas. instead of using point cloud as in existing solutions. This allowed us to learn a lot more about the environment information in which the moments were made. We converted these data into a square image-like form called VDAR and trained our model. The training and validation performance produced quite good results. In our real-time testing environment, we tested the model's responses to moments it had never seen before. The accuracy rate is over 90%. The radar hardware and data capture card used in the study was supported by Beaker company. Special thanks to Dr. Ismail Uzun for his support. In addition, we would like to express our endless thanks to my dear daughters Nehir and Nilnalja, who patiently made all the moments on time and complete manner during the data collection processes. Here you see our references. I can answer your questions if you have any. Thank you for listening.